Okay, let's begin. Here are the references which I used. The main reference is Construction, Dewatering, and Groundwater Control by Powers et al. And second one is Groundwater Lowering in Construction, a Practical Guide to Dewatering, second edition by Cashman and Prim. Okay, I would like to emphasize that the method I'm going to speak about it is based on the analytical method. The analytical design is based on the radial flow to a well. The typical analytical models are in equilibrium. It is assumed that pumping has continued until its zone of influence has expanded to where it has intercepted sufficient recharge from other sources to equal the amount of water being pumped. Of course, many dewatering systems do not reach equilibrium, but the analytical models can, with suitable adjustment, be used to make satisfactory equivalent of non-equilibrium situations. There are also numerical models that you can use, and they can also use for non-equilibrium conditions. We have two different equations. One is for confined aquifers. As you can see in the figure, confined aquifers assume to have constant saturated thickness, is B, and the capital H is the original groundwater head, and a small h is the intended groundwater head after dewatering. The capital R is the radius of influence, and small r, or r sub w, is the radius of the well. And this is for unconfined aquifers. Same thing, but here we have the water table. So capital H is the elevation of the groundwater table from a datum, which usually is a bedrock or an impervious layer. R naught is the radius of influence, and R sub W is the radius of the well. In part one, we only talk about the dewatering for rectangular excavation. Again, to solve the equation in analytical form, we assume that the flow is from a line source to a parallel drainage trench, which a line source is the groundwater outside of our excavation, and trench or water level in the trench is actually the water level that we want to reach. In order to use the proposed analytical models for rectangular excavation, we need to use a circular system with the same area. And to do that, we have to calculate the equivalent radius by this equation. A is the length of the excavation, and B is the width. We also need to estimate the radius of influence. The equivalent radius of influence that appears in the analytical models is a mathematical convenience, because radius of influence terms appears as a log function. Precise estimation is usually not necessary. The most reliable means of estimating radius of influence is by Jacob analysis of a pumping test. But if you don't have a pumping test, empirical relationships can be used. The most common one is the one developed by Sichard and Krielais. I hope I pronounced it correctly, which is give you the radius of influence as a function of drawdown and hydraulic conductivity. Remember, because it's an empirical equation, the units are important. In this equation, both H should be in meters and K must be in meter per second. Now let's do one example. A proposed building has 2 levels of underground parking. The excavation depth is expected to be 6 meters below ground surface. The monitored groundwater level shows that the highest groundwater table is at 3 meters below ground surface. The length and width of the excavation are 20 meters and 12 meters respectively. Hydraulic conductivity from slag test was estimated to be 10 to minus 5 centimeters per second. And we want to know what would be the expected groundwater dewatering to lower the groundwater table 1 meter below the excavation depth, and what would be the radius of influence. The bedrock is at 50 meters below ground surface. Okay, from the assumption in the question, we know that it's an unconfined aquifer. The original water table elevation is 12 meters above bedrock or impervious layer. The final elevation would be 9 meters because we want to be 1 meter, the water table to be 1 meter below the excavated depth. So we want to bring down the water from 12 meter to 9 meter, and we are using the unconfined. So first we calculate the equivalent radius, which would be 8.74. This means if we had the circular excavation instead of the rectangular, the radius would be 8.74. It has the same area as the rectangular. Radius of influence then will be calculated from Sichard equation. As I mentioned, hydraulic conductivity must be in meter per second. So it will be 11.6 meters. And by substituting into the unconfined equation, the dewatering rate for this example will be 6.1 cubic meter per day. But remember, because we have variability in hydraulic conductivity in different parts of the site, we have probably different elevations, bedrock could be different, soil conditions would be different, but in analytical models we only use one value for each parameter. To cover those things, we usually add a contingency factor, which is between 50% to 100%. Some people even using 200%. Depends on the judgment. I usually use 100% for cases that the dewatering rate is small. For example, this case 6.1, I would suggest to use 100% and multiply that by 2. If the dewatering rate is high, for example, is 1,000 cubic meter per day, 50% is usually enough, and multiply that value by 1.5. Don't forget to follow us on Instagram, LinkedIn, and YouTube.